Hello, this is section 16.5 on curl and divergence. Curl and divergence are two examples of differential operators, just like the derivative and the gradient. There's another one called the Laplacian, which we will also explore today. But first let's define what a differential operator is. So a differential operator is a function of a function. In other words, a superfunction. It's a function that takes a function and assigns it to another function. So it takes a function and assigns it to another function. That's what it means to be an operator. Differential operator just means that this is done by taking a combination of partial derivatives. So various combinations of partial derivatives. And these different combinations are what give you the different differential operators. So these functions, so you take a function and you obtain another function. These can be either single variable or multivariable function, and they can either be scalar functions or vector fields. So that is another difference, and that gives you a lot of different possibilities for these differential operators. So the simplest one is called the derivative, which is the first one that you learn in Calc 1. So if you have a function, for example, f of x equals 3x squared plus sine x, the derivative operation assigns this function to another function, which is symbolized f prime of x, which in this case is 6x plus cosine x. So this transformation that takes you from this function to that function is called the derivative, and the derivative is an example of a differential operator. In this case, you have a scalar function, and on the other end, you have also a scalar function. Another one that you learn in Calc 2 is called the gradient differential operator. This applies to a function of two variables. If you have, for example, the function f of xy equals 3x squared plus sine y. Now this is a function of two variables. You can plug it into the gradient operator to obtain the gradient vector, which is now a vector field, indicated by this symbol called the nabla symbol. The partial derivative with respect to x is 6x, and the partial derivative with respect to y of the same function is cosine y. So in this case, this operation takes you from a scalar function of two variables to a vector function of two variables. So these are the two that you have learned so far. We're going to learn a few more today. But first, we need to define just a convenient notation, which is called the nabla vector, N-A-B-L-A, which is symbolized by this upside-down triangle, is the vector of partial derivative operations. And so there's two of them. There's the one in 2 dimensions, partial with respect to x and partial with respect to y, or equivalently in 3 dimensions is a 3-dimensional vector, partial with respect to x, partial with respect to y, partial with respect to z. So it's not a real vector because these are not numbers, these are just symbols for different operations. But this nabla vector can be used very conveniently to define several of these differential operators. So for example, So let's take the first example. If we take f of x, y, z, which is a scalar function, then nabla f of x, y, z is obtained by taking this nabla vector and just adding an f to each one of these components. So partial with respect to x, y, and z of f, which can be symbolized as fx, fy, and fz of x, y, z. So in this case, you start with a scalar function, and you end up with a vector field. So this vector is the gradient of f. So now we can look at a few other examples. So example number 2, now let's start with a vector field. So this vector field in 3 dimensions has 3 components, p, q, and r. So we can take this nabla vector once again, but now because we have a vector field, we can take the vector operation cross product with this. So what we're doing is taking the vector of 3 partial derivatives with respect to x, y, and z, and doing the cross product with p, q, r. And if you compute this cross product using whatever mnemonic you have learned it with, you obtain ry minus qz, pz minus rx, and qx minus py. So this is a 3-dimensional vector field with these 3 components, and this is called the curl of f. So in this case, we start out with a vector, and we end up with another vector. So this differential operator, curl, goes from vector to vector. So let's look at another example. Starting again with the vector field, p, q, and r. So now instead of a cross product, we're going to use a dot product, nabla dot f. So this means we take the vector of 3 partial derivatives with respect to x, y, and z. But now we do the dot, p, q, r. So in this case, what we obtain is the scalar px plus qy plus rz. And this quantity is called the divergence of f. Okay, in this case we start with a vector field, and what we end up with at the other end is a scalar function. And finally, I'll give you one more. So this time we'll start again with a scalar function. So this is a nabla squared f, which is just an abbreviation for nabla dot nabla f. So the divergence of the gradient so you have this vector right here, and you do the dot product with the gradient of f, which is fx, fy, fz. When you do the dot product, this will become the second derivative of f with respect to x, plus the second with respect to y, plus the second with respect to z. And this quantity is called the Laplacian of f. This word Laplacian comes from the mathematician Laplace, who first used this operator. And so here we start with a scalar function, and we have at the other end another scalar function. We'll see later on that it is also possible to do the Laplacian of a vector field, because a vector field simply is a collection of three scalar functions. So we can also take the Laplacian of a vector field, which is just the vector of the three Laplacian of the three scalar functions. So we can mention this here as a fifth example. Starting with the vector field, you can write nabla squared capital F, which is the vector nabla squared P, Q, and R. And this is the Laplacian of F. So in this case, we start with a vector, and you end up also with a vector. Okay, so now that you know the mathematical definitions of these differential operators, let's look at them one by one, and especially what they represent physically. It's important to realize that these differential operators were invented by physicists, not mathematicians, people who were primarily interested in describing certain physical properties of natural phenomena that they were observing. So first, let's look at the curl. So the curl applies to a vector field, and it's a three-dimensional vector field, P, Q, R of x, y, z. Then the curl is the cross product, nabla f, which we saw a minute ago, is a vector whose components are the partial derivatives ry minus qz, pz minus rx, and qx minus py. The curl of f. So this is called the curl. Or it's also called the rotational which is another word that is used in some textbooks. So is a vector field. And as the word curl or rotation symbolize, this represents or it measures the amount of local rotation of the vector field at every point. As you know, a vector field typically symbolizes a velocity field or a force field. Those are vector quantities, and depending on how they interact with each other in three-dimensional space, they may create a vortex or a circular rotation pattern, and that's measured by the curl. So the curl vector has a direction and an orientation and a magnitude like all vectors. So the direction of the curl is perpendicular to the plane, the local plane of rotation. And its direction follows the right-hand rule, or its orientation. So this right-hand rule is the same right-hand rule that applies to the direction of any result of a cross product. It's the way your fingers curl around your right hand. It's also the same way that the direction goes when you're using a screwdriver or a water faucet. Basically, seen from above is positive when it's counterclockwise, and seen from above it's negative when it's clockwise. The magnitude of the vector gives you the velocity of rotation, or the torque if it's a vector force field. So some vector fields have the property that their curl is zero everywhere. Those are called irrotational vector fields. Irrotational, another word is curl-free. And that's if the curl is the zero vector at every point. And so finally, what do we do if we have a two-dimensional vector field? So in this case, F is simply a two-dimensional vector field with components P, Q, and P and Q only depend on X and Y, not on Z anymore. So in this case, we can embed this two-dimensional vector field into three-dimensional space, just considering the XY plane to be the XY plane in the XYZ coordinate system, which means we can just add a third component and make it 0 to obtain this three-dimensional vector field. Because R is 0, then Rx and Ry will also be 0. And because P and Q do not depend on Z, then PZ and QZ will also be 0. And so that means that the curl of the vector field boils down to the first component being 0, the second component being 0, and the third component is Qx minus Py. So it's a three-dimensional vector in which the first two components are both 0. The third component goes in the z direction, which makes sense since the vector field is embedded into the two-dimensional xy plane. Because a curl vector is always perpendicular to the local plane of rotation, it will always go along the z-axis. And this quantity qx minus py, we've encountered it twice already in the gradient field test and in Green's theorem. This is sometimes called the swirl of a two-dimensional vector field F, and it's a scalar. So as an illustration, if we take this vector field right here, which is the vector field x, or minus y x. So the curl of this vector field is 0, 0, and qx minus py, which is 2. So in the xy plane, this would be a vector that goes along the z-axis, so completely vertical, perpendicular to the page, going upwards. At every point, you see that this vector field spins around in a counterclockwise direction. So according to the right-hand rule, the local plane of rotation will always be the xy plane with the curl vector pointing upwards. So moving on to the divergence. Another differential operators. So this one also applies to a vector field. So the divergence is the dot product, nabla dot f, which, as we defined previously, is px plus qy plus rz. So this is called the divergence of f. And it's a scalar function. So that's the main difference with the curl, which was a vector field. This divergence quantity measures the amount of local dilation or compression of the vector field at every point. So dilation is if it's positive. Compression is if it's negative. At every point. So if we look at the sign, it can only be positive or negative because it's a scalar. So if it's positive, that means that there is a local dilation at that point. Another way of visualizing if the vector field is dilating, it means that at that point it looks locally like a source. So it has a source-like behavior. And conversely, if the divergence is negative, that means you have a local compression or a sink-like behavior at that point. Just like in the case of the curl, where some vector fields have a zero curl, some of them have the property of having a zero divergence everywhere. Those are called incompressible vector field. Incompressible or divergence-free. And that's if the divergence of f is equal to 0 at every point. In the case of a magnetic field, the word is sometimes called solenoidal. These all mean the same thing. So now what if we have a two-dimensional vector field? In this case, you only have two components, and each one of them only depends on two variables, x and y. Then the divergence is simply px plus qy, and there's no r in this case. So if we look at another simple example like last time, but this is a different example, this vector field right here is the two-dimensional vector field simply x, y. You see this is a radial vector field. Everything expands outward from the origin. If we calculate the divergence of this vector field, px plus qy is 1 plus 1, which is 2. So 2 is positive, which means that there is a local dilation at every point of this vector field. Every point acts like a source, which means that if you take a little bounded area anywhere in this vector field, so the arrows are moving outwards from the origin. In this case, the arrows are also expanding the further away they are from the origin. And so you have the vector field that is coming in on this side of this region, and it's moving out on the other side. But the arrows that are moving out are bigger than the arrows that are moving in, so the net quantity is moving outwards, which means that you can imagine that there is a local source in here that is producing matter or producing a velocity or force that is moving outwards more than it is moving inwards. That's why this is called a dilation, or a source as indicated by the positive divergence. And so now let's finally move to the Laplacian. So now we're starting with the scalar function f of x, y, z. So the Laplacian of f, as we saw a minute ago, is the nabla squared f, which is the divergence of the gradient of f, fxx plus fyy plus fzz. If this is a two-dimensional vector field, then you would only have fxx plus fyy. So this is used a lot in all kinds of different applications. There's also the same thing as with the curl and the divergence. Certain scalar functions that have the property of having a zero Laplacian everywhere. Those are called harmonic functions. So here's an example of a harmonic function. If you take the function f of x, y, z equals e to the x sine y plus z. So let's calculate its Laplacian. For that, we need to calculate the second partial derivatives with respect to x, y, and z. So we'll do this one by one. F of x is e to the x sine y plus 0. If we do the derivative again, we get another e to the x sine y. F of y is e to the x cosine y. Fyy is minus e to the x sine y. F of z is simply 1. And f of zz is 0. So now if we add these three functions on the right-hand side, we see that the Laplacian of f is 0. Everything cancels out. So this means that this function f that we started with right here is an example of a harmonic function. So the study of harmonic functions is a very large field in physics and in mathematics called harmonic analysis. So now that we've defined all of these operators, let's look at some of the properties. So first of all differential operators are linear. Linear operators, meaning that they preserve addition and scalar multiplication, which means that you can always float out scalar constants and break up sums or subtractions. For example, if you have the curl of a sum of two vector fields, f plus g, you can always just take that as the curl of f plus the curl of g. Or if you have the curl of some constant times the vector field f, you can float that constant outside of the curl operator. The same kind of thing that you are used to doing with regular derivatives, which is another example of a linear operator. So you can take these differential operators and mix and match them to get all kinds of interesting properties. So for example, if you take the divergence of the curl of f. In this case, you get 0 for all vector fields f. So another interesting property is if you take the curl of a product of a scalar function f with a vector field f, this becomes f of the curl of f plus the gradient of f cross f, some kind of a extension of a product rule. You have a similar one with the divergence. So the divergence of a scalar product f times f is equal to f times the divergence of f plus the gradient of f dot capital F. Another one that's even less obvious is if you take the curl of f, this becomes the gradient of the divergence of f minus the Laplacian of f. So there's several other interesting properties. You can discover some of them in the exercises. Some of these are more obvious than others, but you can always just prove them easily. If you want to prove number 2, for example, all you've got to do is rewrite everything in terms of components. So for 2, if you have a vector field f with components p, q, r, then the divergence of the curl of f is the divergence of the curl of f, which we know is ry minus qz, pz minus rx, qx minus py. So the partial derivative of the first component with respect to x is ry minus qzx plus pz minus rxy plus qx minus pyz, which is ryx minus qzx plus pzy minus rxy plus qxz minus pyz. So if you recall that pyz and pzy are the same thing, you see these two terms cancel each other. Same thing with qzx and qxz and ryx and rxy. And this is by Clairaut's theorem. Which is a theorem that says that if you have a mixed second partial derivative, it doesn't matter in what order you take the two derivatives. And you can explore the proofs of these other theorems by doing the same thing. You just take the vector field f and rewrite it in its terms of its components p, q, and r, and just proceed through with the calculations to get the proof.